Hello and welcome to this chemistry lecture series. In this video, we're going to take a look at chapter 16.2, which is now going to address the first of two different types of reactions that we're going to see for halogenoalkanes, and that is the nucleophilic substitution reactions of the halogenoalkanes. So let's get started with this topic. Now, halogenoalkanes are extremely reactive because of the polar bond created between the carbon and the halogen. So we kind of touched up on this in the earlier section, but when you have a carbon bonded to a halogen, the electronegativity of the halogen is really high, whereas the electronegativity of the carbon compared to other nonmetals is pretty low. So the high electronegativity of the halogens compared to the low electronegativity of the carbon creates a polar bond where the halogen is partially negative and the carbon is partially positive in charge. As we have said before, polarity in organic chemistry is what creates reactivity. The polar nature of the carbon-halogen bond makes it very attractive to both nucleophiles. Actually, we're just going to stick with nucleophiles right now, although there are some electrophilic reactions. But it makes it really reactive, really attractive to nucleophiles. It leaves what we say the carbon wide open for nucleophilic attack. So remember what a nucleophile is. Nucleo meaning nucleus or positive, philic meaning loving. So nucleophiles are things that are going to be attracted to positive charge in organic compounds. So nucleophiles will have two things. The first is a lone pair, and the second is some kind of negative charge, either fully negative or partially negative. So a nucleophile is going to have a lone pair of electrons and a partial negative charge. So what happens during nucleophilic substitution reactions is that a nucleophile, and there are three different types of nucleophile we're going to see in this section, but we'll just stick with Nu right now, which just represents a nucleophile. A nucleophile will get too close to this carbon-halogen bond, and because of the partial positive charge on the carbon, that nucleophile will be attracted to the carbon. So as we can see here, symbolized by this this curved arrow, the nucleophile will use its lone pair of electrons to bond to the carbon in the halogenoalkane, therefore kicking out the halogen. So during these nucleophilic substitution reactions, the halogen gets replaced with a nucleophile. So we'll put it here. Where is this? A halogen gets substituted with a nucleophile. But that nucleophile can change. There's three different, like I said, there's three different nucleophiles that we're going to see here. But this is always the case with these nucleophilic substitution reactions. Halogen gets kicked out, nucleophile comes in because of its attraction to the partially positive carbon. So let's look at the details that happen here. The first and most common reaction we're going to see is the substitution reaction of a halogenoalkane with an aqueous alkali. So remember, alkalis are water-soluble bases. So the term alkali here is a water-soluble base. And the most common alkalis are always going to be NaOH, sodium hydroxide, or potassium hydroxide, KOH. In this case, we have chosen sodium hydroxide as the example, but understand that this reaction could happen with potassium hydroxide very easily. So when halogenoalkanes react and are heated with sodium hydroxide or possibly potassium hydroxide, the nucleophilic substitution reaction happens. Here We have halogenoalkane and sodium hydroxide underlined because they're our reactants. But this reaction does have a condition, that condition being that the reaction is heated. So we do need to, in that double underline, have conditions here present. So not only do we just mix halogenoalkanes with sodium hydroxide, those two reactants need to be heated in order to get a nucleophilic substitution reaction to happen. Now, what is a nucleophilic substitution reaction? We just talked about it. It is a mechanism for an organic reaction where a nucleophile is going to attack the carbon in the halogenoalkane, and it's going to replace or substitute the halogen because the carbon carries that partial negative charge. Partial positive charge. During the reaction, what ends up happening is that the halogen gets replaced with a hydroxyl group, because when we use sodium hydroxide or potassium hydroxide, when we use an alkali in this reaction, the nucleophile for that alkali is going to be the OH ion. So in this particular scenario, the nucleophile is going to be the hydroxide ion. So the hydroxide ion comes in, kicks out the halogen, and introduces a hydroxyl group to the organic compound, making it an alcohol. So the alcohol here is bolded because the alcohol is going to be our product. So in this particular scenario, in this particular reaction, this is a reaction where a halogenoalkane gets converted, and we'll put it, actually we'll have it right here, where halogenoalkane gets converted to an alcohol. I've talked about before about seeing organic reactions as the conversion of one functional group into another. Well, in this particular reaction, we're converting a halogenoalkane to an alcohol by using sodium hydroxide and heat in order to do the nucleophilic substitution reaction. The reaction also creates sodium halides, meaning something like sodium chloride or sodium bromide, depending on what our halogenoalkane was. But in reality, this sodium halide, this NaX, is really just a sodium ion floating around aqueous with a halide ion, X minus aqueous. Remember, ionic compounds that are soluble in water when they're aqueous are really just their ions floating around in solution. So this is what the reaction is. So let's look at a specific example. Here we have, in this case, this is 1, 2, 3, 4, 5. So this is 3-bromopentane. 3-bromopentane is a halogenoalkane. And here we have the 3-bromopentane shown in different ways. We have it as a skeletal formula. We have it as a structural formula. The 3-bromopentane can react with sodium hydroxide when it's heated. And what's going to happen is that that bromine is going to be substituted. It's going to be exchanged for a hydroxide. And then the sodium and the bromine ions are going to go off and be aqueous. So we can put it as NaBr aqueous, or we could put it as Na plus aqueous plus Br minus aqueous. So we can do either or. So it's either NaBr or Na plus aqueous plus Br minus aqueous. And in fact, we're going to see what another way of doing it right here is. So that's what happens during a nucleophilic substitution reaction. The bromine, or the halogen, whatever it is, chlorine, bromine, iodine, is going to be replaced by the hydroxyl group, OH minus, because the nucleophile in this particular reaction is hydroxide. So we're going from a halogenoalkane to an alcohol. We can see the exact same thing happening with the structural formula, CH3, CH2, CH, Br, CH2, CH3. The Br will simply just get substituted with an OH in the organic compound, and then NaBr will be made. Now, one of the things that you need to be aware of is that a lot of the time we do like to use ionic equations in chemistry. So the ionic equation here will just be the exact same either skeletal or structural formula, but because the sodium is aqueous sodium ions in the reactants, NaOH aqueous means aqueous sodium ions and aqueous hydroxide ions, and aqueous sodium and bromide ions in this case in the products. The sodium ion is a spectator ion, meaning it can be cancelled out. And in that case, we'll just simply end up with CH3, CH2, CHBr, CH2, CH3, plus OH minus, which is our nucleophile, which is going to replace the bromine in our halogenoalkane, creating our alcohol, which in this case will be 3-pentanol, because that alcohol is in the exact same carbon, 3, as the bromine in 3-bromopentane, and our bromide ion. And the bromide ion will just be bromide ion, not sodium bromide, because this is a net ionic equation. So that's a reaction. That's a reaction that happens between halogenoalkanes and sodium hydroxide or potassium hydroxide, possibly, because it's also an alkali, when they're heated. Now let's talk about that. Let's talk about heating here. Now this reaction can also be seen as a hydrolysis reaction of halogenoalkanes. Why? Remember the term hydrolysis. Hydro means water. Hydro is water, although it can also mean an acid or base, because they are reactants with water and they're in water. And lysis means breaking. So these reactions can be seen as a hydrolysis of halogenoalkanes, because when we do this, we are breaking, and let me quickly go back to the prior slide, we are breaking here the halogen and carbon bond. So if you notice here, the carbon-hydrogen bond gets broken, hydroxide comes into the carbon, and then the bromine is going to be by itself, or the sodium in this case, but it's going to be separated from the halogen, the organic. And because of that, because we are breaking off the bromine, this could be seen as a hydrolysis reaction. Let's go back. Oops. So this could be seen as a hydrolysis reaction. And in fact it is. Remember, hydrolysis means the breakdown of a compound by water, but also used to describe the breakdown of a compound by either a dilute, acid, or alkali. Why dilute? Why is this term so important here? The term dilute means in water. So because the term dilute means in water or aqueous, so it's in water, or aqueous essentially, it means that the dilute acid or the dilute alkali it's not reacting by itself. It's usually a catalyst or some kind of way of easing a reaction with water. What the alkali or acid, depending on which one you use, do in this situation is speed up the reaction of the halogenoalkane with water, which it will have normally, even if the acid or base was not present. Hydrolysis of halogenoalkanes with water can also happen, but it's a lot slower. The hydroxide ion that we just talked about is a much stronger nucleophile because it has it's a much weaker nucleophile because it has a partial positive charge than the hydroxide ion. So water molecules are weaker nucleophiles, making the reaction happen a lot more slowly if we're just using water. Whereas if we use the alkali, the hydroxide ion, the reaction happens much faster. So if we have here, for example, bromoethane reacting with water, we're still going to get the same reaction. We're still going to have that Br get kicked out of the halogenoalkane, become Br minus, and the water is actually going to break apart. You're going to get the hydroxide that comes from the water, the OH that comes from the water, creating the alcohol instead of the halogenoalkane. And then also the hydrogen from the water, and I guess I can do this, with creating a hydrogen ion. But again, this is not going to be as quick, it's not going to be as fast as using the hydroxide ion. The hydroxide ion speeds up this whole reaction because it is a much stronger nucleophile than the water itself. Now, both of these reactions do have to happen under what we call reflux or heating. Reflux can be essentially interchanged in organic chemistry with heating. Why? Reflux is a way, it's a cooling technique that allows us to heat up mixtures that would otherwise evaporate during heating. So things that are volatile, things that easily vaporize, easily like most organic compounds are very volatile. So things that are volatile are going to easily vaporize, meaning if we heat them up, they become gases and they evaporate away. But with reflux, we can actually heat up volatile organics and not lose a lot of them. So how does reflux work? Well, what we would essentially do is mix our two reactants into a vessel, into some form of flask. So in this case, our reactants will be the halogenoalkane and the alkali, the hydroxide, sodium hydroxide, for example. And then we will heat them. The problem is that as we heat this, the halogenoalkane, which has a very low boiling point, because it's very volatile, would start to evaporate. So the gases of that halogenoalkane will start to come out and they'll go up this tube, which we use for reflux. Now, this is what we call a condenser tube. What the condenser tube does is that as this gas goes up into the condenser tube has two sections to it. There is the inside tube, which is where the gas is going to go through. And then there's an outside sleeve to the tube, which we're pumping water in one side and it's coming out the other. As this gas evaporates through the condenser, because of the water, has lower temperatures. It cools down our gases. And so the gases don't get to make it all the way out of the flask. As they go into the condenser, the temperature drops, those gases start to condense back into our mixture. So what the condenser tube does, and this whole process is called reflux. What the condenser tube does is that it cools down the gases of the volatile liquid so they can fall back into the reaction mixture and keep reacting. So this allows us to grab volatile liquids like most organic compounds and heat them up without losing the majority of our reactant to evaporation. That whole process is called reflux, and it's very important in organic chemistry. A lot of the time, when we say that a reaction is heated, like we just did with this reaction, in reality we're saying we're doing it under reflux, because that's how we heat up organics. So if we go back, you might have noticed that this reaction said heated. In reality, this is not heated, it's more reflux, meaning that we heat it up in a reflux setup, in the one that we just saw. All right? So that is how we carry out this reaction, whether it's with water or with the alkali, or even with a dilute acid. This reaction is carried out under reflux, so we can heat up those volatile organics. Now, there's an actually very interesting way of testing how quickly this reaction happens. So we established that hydrolysis reactions with halogenoalkanes are going to happen, whether we use water, an alkali, or an acid, they're going to happen. But they actually happen at different rates, not depending on what we use, although obviously the water would be slower, but depending on which halogens we have present in the halogenoalkane. So which halogen the halogenoalkane has actually makes a difference in the rate of the reaction. During the hydrolysis reaction, you might have noticed that a halide ion is made. So if I go back, whether I use water, where I make a bromide ion in this case, a halide ion, or whether I use a hydroxide, an alkali, and again, I'm making that halide ion, that Br minus, I'm going to make a halogen ion during the hydrolysis of halogenoalkanes. We can use that fact to figure out which halogen gives the quickest reactions, which halogen has the fastest rate of hydrolysis reactions. And we can do this because in chapter 12, when we're studying halogens, we learn of the reaction of the halogens with silver ions. We learned that when you combine a halogen ion with a silver ion in solution, and we'll put X minus here, the resulting compound, the silver halide that's created, is going to be solid. It's going to be a precipitate. So we can use that to our advantage and combine organic chemistry with inorganic chemistry. So if we do the hydrolysis of a halogenoalkane, and again, here we're using X to symbolize a halogen. This could be chlorine, bromine, iodine, or fluorine, although fluorine is rarely seen. So X could be either chlorine, bromine, iodine, or rarely fluorine. When we react it with water or with an alkali, what we're going to get is our alcohol here being created, hydrogen ions if we use water, sodium ions if we use sodium hydroxide, and the halide ion that is created. Well, that halide ion, if we add silver ions to this mixture, that halide ion would react with the silver ions. So this will essentially form what we call a secondary reaction. As the halogen reacts with water or with alkali to form the alcohol, the halide ion is created. If we have silver ions into a mixture, the halide ion will then go and react with the silver ions to create a precipitate of silver halide. And as we saw in chapter 12, if that halogen is chlorine, then that precipitate will be white. If that halogen is bromine, then the precipitate is off-white. And if the halogen is iodine, then the precipitate is a pale yellow. So we are going to use this secondary reaction to gauge how quickly the hydrolysis of the halide ion happens. Why? This gives us a visual. The precipitate is a visual that we can rely on. Usually when the halogenoalkane reacts with water and it creates the alcohol, the halide ion, in this case hydrogen ions, we don't have any visual representation of what that or how quickly that reaction is happening. But by adding silver and creating a precipitate, the precipitate is now visible. It's an observation. We can see the precipitate being formed. So we can test how quickly this reaction happens. Because the more quickly this reaction happens, then the more quickly the halide ion gets made, and the more quickly this reaction happens. Because one reaction feeds into the other one. As the halide ion gets made, automatically, really quickly, it will react with the silver to create the precipitate. So the faster the precipitate gets made, the faster the hydrolysis is happening. So let's look at the result of doing that. When we run this test with 1-chlorobutane, which is butane, remember, is 4 carbons, so 1, 2, 3, 4. And this is 1-chloro, so on carbon 1 there's a chlorine. So that's 1-chlorobutane. 1-bromobutane, so same thing, 1, 2, 3, 4, with a bromine on carbon 1. And 1-iodobutane, same thing with an iodine on carbon 1. So if we use the exact same halogenoalkanes, but with the halogen being different, if we react this with water, we can see that the 1-iodobutane will react the fastest, it will create the precipitate the fastest, while the 1-chlorobutane reacts the slowest out of the 3 halogenoalkanes. We can see that in this graph, and I'll show you this video in a second, but we can see that in this graph. So this is a graph of time versus absorbance. Absorbance is a way of looking at color or precipitate. It's a method where we shine light or a laser through a solution, and the darker the solution gets, the higher up the absorbance of the light becomes. So higher up means more color, more opaque. So if we look at these reactions, when we use 1-iodobutane, that absorbance skyrockets. Let me use a highlighter here. The absorbance when we use 1-iodobutane is high. It skyrockets. As soon as this reaction happens, we have a lot of absorbance, meaning that the precipitate is created very quickly. Whereas with the 1-bromobutane, that absorbance does go up, but it takes a lot longer because the precipitate gets created more slowly. And finally, if we use 1-chlorobutane green here, that takes so long, it looks like a horizontal line. Why? Again, because the 1-iodobutane is going to react, or undergo hydrolysis a lot faster than 1-bromobutane, which is even faster than 1-chlorobutane. So let's see that in real time. We're going to see a visual of this reaction happening here in the video. Whereas in this video, we have, going from left to right, 1-chlorobutane, so this is the Cl1, 1-bromobutane, so this is the Br1, and 1-iodobutane, which is I. Now, pay attention, be careful with this one because it does have a bit of a glare, so it looks like there's a solid, but you'll see the solid later. But look at how quickly, once the water is added, the precipitate for the iodine gets created, the 1-iodobutane gets created versus the one for the chlorine. So we're going to play that right now. So pay close attention to the beakers. So there the water is created. And then look at how quickly the yellow in the iodobutane gets made. And then the bromine and then the chlorine. So they're going to replay this again in a second. So again, notice how when the water gets added, which we'll see in a second here, we add the water. The 1-iodobutane reacts really quickly. You start seeing the yellow. Then the 1-bromobutane, then the 1-chlorobutane gets those precipitates. Because the 1-iodobutane undergoes hydrolysis much quicker. What you're seeing here, that color, that is the silver precipitate being made. So for the iodine, the 1-iodobutane, that's silver iodide solid being made, which is yellow. For the bromine, 1-bromobutane, the silver bromide, which is an off-white precipitate. And then for the chlorine, silver chloride, which is a white precipitate. These are S's. I just messed up the S a little. But that's what we're looking at here. That graph spiking, that represents the precipitate for the 1-iodobutane being made so quickly, which is why these spikes, the more precipitate we have, the more it absorbs light because very dark, very opaque. So that's the result of this lab. But why does this happen? At a chemical level, why does one iodobutane react so much more quickly than one chlorobutane if the only difference is which halogen we have in the reactant? Well, that's where bond strength comes in. So this is going to go back, probably a good thing to start reviewing now because the exam is so close, but this is going to go back to our bonding and enthalpy section. So what happens? The result of the silver nitrate test that we just saw can be explained by bond strength of the carbon-halogen bond. When that reaction happens, what essentially happens is that in our halogenoalkane, our CX bond, and now obviously we have like 3 other things here, but we don't care what they are. Our CX bond in the halogenoalkane is broken, which creates the COH, that alcohol, plus the halide ion. The halide ion then reacts with the silver ion and creates the silver halide solid. Well, in order for all of these to happen, what needs to happen first is that this carbon-hydrogen halide bond needs to be broken. We need to break that carbon-halide bond. That breakage is where our activation energy is used. We use the activation energy of this reaction to break the carbon-halide bond. The bond energies then play a key part here. Why? As we go down the group from fluorine to chlorine to bromine to iodine, the carbon-halide bond, or is the bond energy, is going to decrease. So the carbon-halogen bond energies are going to decrease as we go down the group. And the reason for this is that the radius of the halogens increases. So as we go down the group, fluorine is small, chlorine is a little bigger, bromine is a little bigger, and iodine is the biggest out of all of them. And they're all bonded to carbon. So what happens? As the atoms of the halogens get bigger, the distance from the nucleus of that halogen to the bonding electrons right outside that atom that are bonding it to carbon is going to increase. The bigger the atom is, the bigger the distance between the nucleus and the electrons. That is what weakens the bond. Because remember, the farther two things are from each other, farther two charged particles are from each other, the weaker their attraction. So because the carbon-iodine bond has the most distance between the nucleus of the iodine or the halogen to the bonding electrons, because the radius of iodine is the biggest, it's going to have the weakest bonds. It's going to have the smallest bond energy. The smaller the bond energy is, the lower the activation energy we need to break the bond is, and the faster the reaction can happen. That's why the reactions happen more and more quickly as we go down the halogen group. As we go down the halogen group, the radius of the halogens goes up, which means the bonds are going to be weaker, the bond energy is smaller, which means the reaction can happen faster. It goes faster as we go down the group. And again, this is just going back to enthalpy changes and bond energies that we studied in chapter 6. So as you can see, all of this is connected. Organic chemistry, inorganic chemistry. This one reaction explanation has all 3 of them. It has organic chemistry in the form of the hydrolysis of the halogenoalkane. It has inorganic chemistry in the form of the reaction between the halide ion and the silver ion to create a silver halide precipitate. And it has physical chemistry in the explanation as to why the reaction of hydrolysis speeds up. The fact that as we go down the group, the atoms of the halogens get bigger, which means the distance between the nucleus and the bonding electrons gets bigger, meaning the bond energies get smaller, and so the reaction can happen more quickly because the activation energy is smaller. So that's the whole explanation behind why hydrolysis reactions happen more quickly as we go from fluorine to chlorine to bromine to iodine. All right. So again, this is all an explanation based around a nucleophilic substitution reaction, where if we go back, where it's a nucleophilic substitution reaction or a hydrolysis reaction, it's really both, where a halogenalkane reacts with an alkali or water to form an alcohol. Well, these hydroxide ions, hydroxide ions are not the only nucleophile. Water can also react like this, hydroxide ions react like this, but there are two other nucleophiles we're going to study in this class that undergo a substitution reaction with halogenalkanes. The first one we're going to look at is cyanide ions. And this is very similar to the reaction of hydroxide ions with halogenoalkanes. The cyanide ion is also a negatively charged ion. It's a carbon triple bonded to a nitrogen, where both the carbon and the nitrogen have a lone pair of electrons, meaning that the carbon carries a negative charge here. That's why the negative charge on cyanide, which we normally write as Cn-, comes from. When a halogenoalkane reacts with a cyanide ion mixture, and we're going to look at what that is now, the cyanide ion acts like a nucleophile, creating the same reaction we saw earlier. So the halogenoalkane is reacted with potassium cyanide, so KCN, also known as rat poison. So with potassium cyanide, the halogenoalkane can react, but the potassium cyanide has to be ethanolic. And this is a new, essentially a condition here, but ethanolic potassium cyanide, meaning it's reacting with KCN, but that KCN cannot be in water. So ethanolic, not aqueous. So what is ethanolic? Ethanolic means dissolve in ethanol. So instead of using water as a solvent for the solution, we use ethanol. Why? Why would we use ethanol instead of water? Well, it's very simple. We saw earlier that water is also a nucleophile. If we use aqueous potassium cyanide, the water would act as a nucleophile and we will get an alcohol out of the reaction. So because water is also a nucleophile, a reactant with the halogenalkanes, we avoid it as a solvent. That's new. It's kind of unique to organic chemistry because up to now everything has been in water. But we have to realize that in organic chemistry, sometimes water is a reactant and reacts with other compounds. So because halogenoalkanes react with water in hydrolysis, we have to use ethanolic potassium cyanide if we want the halogenoalkane to react with the cyanide ion instead. And this reaction also needs to be carried out under reflux. We still have those conditions here. So the reaction for potassium cyanide and ethanolic reacting with halogenoalkane is going to happen in reflux as a condition. So here in blue we have our reactants, the halogenoalkane and that ethanolic potassium cyanide. So KCN. The reaction is going to do the same thing we saw earlier, only instead of replacing the halogen in the halogenoalkane with a OH to make an alcohol, it's going to replace it with a CN group, a C triple bond N group, meaning we're going from a halogenoalkane to a nitrile. This is actually a very useful reaction in chemistry because it is one of the few reactions where we can easily add a carbon to a halogenoalkane or a starting material. So it's very useful in industry whenever we're one carbon short in the products. Again, the product of this reaction is going to be a nitrile. So this is a reaction where we convert a halogenoalkane to a nitrile, adding a carbon to that original starting material, to the original compound. So here, for example, we go from and again, we have, well, actually, look at the structural formula. We have 1, 2, 3, 4 carbons. So this is, I'll write it on here. This is 4 carbons, so it's prop. So this is 1 chloro, because it has chlorine, propane. And if one chloropropane or any halogenoalkane reacts with KCN, potassium cyanide, in ethanol, the cyanide ion will act as a nucleophile, replacing the chlorine and creating this right here, this nitrile, which has 1, 2, 3, 4, and then a 5th carbon here with a CN. That 5th carbon coming from the cyanide ion. So it is adding a cyanide. The other product here that happens is going to be the KCl, potassium chloride. The potassium coming from the KCN, the potassium cyanide, and the chlorine coming from the halogen that was kicked out of the halogenoalkane. So exact same reaction really, exact same nucleophilic substitution reaction, but we're using potassium cyanide to introduce the cyanide ion as the nucleophile, and we are doing this in ethanolic potassium cyanide, so we don't introduce water, which would react with the halogenoalkane. Now finally, the other type of nucleophilic substitution reaction is going to happen with ammonia. So in this particular case, ammonia, NH3, would be our nucleophile. So the ammonia would react with halogenoalkane. So we're going to have our reactants in that. Our halogenoalkane reactant, which obviously, because this is the halogenoalkane chapter, is going to react with our ethanolic ammonia. Again, why ethanolic? Why is it in ethanol? Because if we had it in water, if we had it aqueous, the water would react. So those are going to be our reactants: ethanolic ammonia and halogenoalkane. Now, this reaction does have 2 conditions, not just one. It does need to be heated, meaning under reflux, like the cyanide reaction or the alkali reaction. But apart from the condition being that it needs to be under reflux, it also needs to be under pressure. The nucleophilic reaction, the nucleophilic substitution reaction with ammonia does not only need heat, it needs pressure. Because ammonia is going to want to become a gas, which we cannot let it happen. So we need pressure to keep that ammonia dissolved in the ethanol. The reaction substitutes the halogen for an amine group. Do notice that the ammonia is going to lose a hydrogen when it does this. Oops. And it becomes not an ammonia, NH3, but an amine, NH2. So the ammonia is going to become NH2 and be replacing our halogen, creating a primary amine. Primary meaning that it's NH2, not N with carbon chains on it. Now, the idea of primary amines is one that we're mostly going to discuss in A-level chemistry, but we do need to realize that this is going to create an amine with we have an H2 and not a substituted amine if we use ammonia. Now, if the ammonia is not in excess, the products can become nucleophiles as well. So notice that this reaction says excess ammonia. And so we need this ammonia to there be a lot of ammonia. The ammonia is going to produce the iodine, and create the NH2 in the products, whereas the iodine goes with the hydrogen the ammonia loses and creates HI in this case. If it was chlorine instead of iodine, it would be HCl. So when this happens, so we need to make sure that this ammonia is in excess. Oops, let me make it smaller. So this ammonia needs to be in excess. In order for us to go from that halogenoalkane to a primary amine, we need to have an excess of ammonia. Why? If we don't, what can happen is that our products will be involved in a reaction. This is 1, 2, 3, 4. So this amine butane or butanamine can act as a nucleophile as well. Remember that this nitrogen right here, which only has 3 bonds, has a lone pair of electrons and a partially negative charge, which makes this compound a nucleophile. Now, it's not as strong as a nucleophile as ammonia, so as long as we have enough ammonia, the ammonia will react. But if we run out of ammonia because we do not have an excess, this product can act as a nucleophile itself, reacting with a halogenoalkane and creating a multiple substituted amine or a secondary amine. Why is this secondary? Notice we have the nitrogen and we have the 4-carbon chain from the halogenoalkane, but when that product acts like a nucleophile, so this product can do the exact same thing that the ammonia did. It's going to attack the halogenoalkane. It's going to lose a hydrogen, attach a nitrogen to the carbon, and now it has a second carbon chain. And that creates what we call a secondary amine. Why secondary? It has 2 different carbon chains. 1, 2. So it's secondary. So this is why we need to use an excess of amines, of ammonia. Sorry, amines where one of the hydrogens or on the nitrogen is being replaced are called substituted ammonia amines or secondary amines because we have multiple carbon chains on them. Again, this is more of an A-level topic, but you do need to be aware for the AICE exam that if we don't use an excess of the ammonia, these multiple substituted amines or secondary amines can get created. And we could even create tertiary amines if we were to replace this hydrogen with, again, another carbon chain from the halogenoalkane. So this is another nucleophilic substitution reaction that can happen with ammonia. So there are 3 reactions that we ended up with for nucleophilic substitution, or 4 depending on how you see it. The one with the alkali, where we create an alcohol, or water, where we create an alcohol, which is up here. Let's go all the way back. So the reaction of the halogenoalkane with sodium hydroxide or an alkali under heat to create the alcohol. There's the reaction of the halogenoalkane with water, which will create the exact same products, only hydrogen ions instead of sodium ions. There is the reaction of cyanide ions or potassium cyanide ethanolic with halogenoalkanes to create a nitrile. And then there's a reaction of halogenoalkanes with an excess of ammonia in ethanol to produce a primary amine. And if we do not have an excess of ammonia, then we would also react that primary amine product with the halogenoalkane to create a secondary amine, which just essentially replaces the hydrogen on the product with another carbon chain from the halogenoalkane. And that's it. That is it for section 2 of chapter 16 and the halogenoalkane reaction, substitution reactions. We'll see you in the next video to discuss the mechanism for these reactions.